Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum, dear students. In today's lecture, we are going to study about the soil compaction part 2, remaining part, which was the lecture number 9. In our previous lecture, we focused on the laboratory tests. We discussed the standard Proctor test and the modified Proctor test. We also solved a simple problem number 1 related to the standard Proctor test. We also discussed the compaction effort, the compaction energy transferred to the soil in standard Proctor test and modified Proctor test. And at the end of the previous lecture, we made a comparison between the standard Proctor test and the modified Proctor test. In today's lecture, we are going to focus on the compaction equipments and the field compaction tests needed are performed to check whether the desired compaction is achieved or not. So there are 3 methods which are used in the field. One is the sand cone method, predominantly that one is used, and rubber balloon method, nuclear density meter method is also currently used in the field. We will solve a problem 2 which is related to the sand cone method. So starting with the stage 2 of the compaction equipment, the desired level of compaction is achieved by matching the soil type with its proper compaction method. Other factors must be considered as well, such as the compaction specification, that how much we need to compact, what would be the dry density, what would be the dry unit weight of the compacted soil, and it also depends upon the job site condition. For example, if we are having a wide and open area, so large compactor like the sheep foot rollers or the smooth wheeled rollers are preferable. And if we are dealing with a congested area such as the trench or the trench backfills, then the vibratory hammer are more widely used in the field. Discussing the soil type, for the cohesive soils, like clay is a cohesive and its particles stick together, therefore a machine with a high impact force is required to ram the soil and force the air out, arranging the particles. So a rammer or a sheep foot roller is the best option to compact the cohesive soils. For granular soils, since granular soils are not cohesive, the particles require shaking or vibratory action to move them, to rearrange them, to realign them. So vibratory plates are the best choice if we are dealing with a small amount of work. Smooth wheel, smooth drum vibratory rollers are appropriate for higher production work for the granular soils. Now in the past, method A was used and currently method B is used for the compaction specification. In method A, detailed instructions about the machine type, left depths, left is the thickness of the soil layer, which was compacted using different types of rollers. Number of passes, speed, and moisture content were recorded. Recipe is given as a part of the job specification to accomplish the compaction needed to achieve the dry density or the desired unit weight, dry unit weight. This method is outdated as machine technology has far outpaced common method specification requirements. Nowadays, end result specification is desired. For example, if you want to achieve the dry unit weight, dry density or the dry unit weight of that particular soil, we don't worry about what type of roller they are using, but we care about the end result specification, which are the dry density and the dry unit weight. So final compaction requirements are specified. It will give more flexibility in determining the best and the most economical method of meeting the required specification of compaction. Now this will allow the contractor to take advantage of the latest technology available. Now what are the different types of rollers which are used? Smooth wheel roller, pneumatic or rubber tire rollers are used in the field to compact the soils. Sheep foot rollers, vibrating drum on smooth wheel roller, handheld vibratory plates, and handheld the vibratory rammers are used in the field to compact the soil. So starting with the smooth wheel roller. Smooth wheel roller cover the 100% area under the wheel, as you can see here, and the wheel is smooth. The contact pressure applied onto the soil is approximately 380 kilopascal, and these types of rollers can be used on all soil types except for rocky soils. Compactive effort is static. The most common use of large smooth wheel roller is for subgrades and compacting asphalt pavement. These types of rollers are suitable for well-graded sands and gravels, silts and clays of low plasticity, but they might not give you good results in uniform sands, silty sands and soft clays. Pneumatic type rollers are used for highway fills or earth dam construction. 80% coverage area under the wheel, as you can see there are some spaces in between those wheels. Contact pressure is 700 kilopascal, and 7 to 3 wheels are arranged in 2 rows, in the front row and the back row. Compaction effort is static, suitable for the coarse and fine grained soils, but might not give you good results in very soft clays and highly variable soils or poorly graded soils. Another type of rollers are the sheep foot rollers. As you can see, certain protrusions on the smooth wheel type of rollers you can observe in here. Round or rectangular shaped protrusions are feet attached to a steel drum. 8% or 8 to 12% coverage area is there. As you can clearly see that these protrusions are applying significant amount of pressure, which is close to 1400 to 7000 kilopascal. It is best for clay soils. Compactive effort is static, suitable for sands and gravels with greater than 20% fine grained soils. but might not give you good results for coarse soils and uniform gravels. There is another type of roller, which is vibrating drum on smooth wheel roller. That vertical vibrator attached to smooth wheel rollers, and the best explanation of why roller vibration causes densification of granular soil is that the particle rearrangement occurs due to the cyclic deformation of the soil produced by the oscillations or the vibrations of the roller. Now these vibrators can be attached to the smooth wheel roller, pneumatic rubber tired rollers or sheep foot rollers to provide the vibratory effects to compact the soil. So there are off-center rotating weights which will cause the vibratory action in the smooth wheel roller or pneumatic rubber tired rollers or sheep foot rollers, which will densify and compact the soil beneath this vibrating drum on smooth wheel or any type of roller. The compactive effort is static, suitable for granular soils. Handheld vibratory plates are also used for limited area of work. So this is the important point: soils with low to moderate fines content. The suitability and the compaction is achieved for soils with low to moderate fines content, unsuitable for large volume of work and wet clay soils. Handheld vibratory rammers are also used. They are also known as trench tamper, hand guided pneumatic tamper, suitable for trench backfill work in confined areas, unsuitable for the large volume of work. To compact the soil, it will take a lot of time. Moving towards the field compaction tests, which was the stage 3, that now we need to verify the stage 2 work done by the compaction equipments, and also compare with the stage 1 the lab tests performed on the soil. So we obtained the unit weight or the density, dry density from the lab tests, and after that we compact the soil. Now we need to verify that whether this compaction, which is done in the stage 2, is done properly, and how we can verify that. We need to compare the dry density and the dry unit weight values which are obtained in the field. Now in most specifications for earthwork, the contractor is instructed to achieve a compacted field dry unit weight of 90 to 95% of the maximum dry unit weight determined in the lab, which is the stage 1, by either the standard or modified Proctor test. This is a specification for relative compaction. Now what is a relative compaction? When we are comparing the dry unit weight which is obtained in the field using sand cone method, rubber balloon method, or nuclear density meter. If you compare the unit weight which is obtained in the field with the unit weight or the maximum dry unit weight which we obtained in the lab using standard Proctor test and modified Proctor test, Now we discussed in the end result specification that the contractor can use different types of rollers or heavy rollers. What we need to care about is that the contractor has achieved the relative compaction in most cases greater or equal to the 95%. Here an example is given that the maximum density at the optimum moisture content is 100%, which is obtained from the lab tests. Now the contractor can reach to the 98% at W1 or W3, this is the moisture content, or at the optimum moisture content, which is the W2. This will be the 100% compaction, or the maximum density is achieved at the OMC. Now the contractor can reach to the 98% using the water content W1 or W3, and we can verify the 98%, 95% or 90% relative compaction once we perform the field compaction tests such as sand cone method, rubber balloon method or nuclear density meter. So the contractor must be in this range if we give them the specification that you need to achieve the 98% maximum dry density value. There are several factors that must be considered to achieve the desired unit weight of compaction in the field. We already discussed several factors, but we are going to reinforce that water content, soil type, thickness of the lift or the soil layer which is being compacted, intensity of the pressure applied by the compacting equipment or different types of rollers, the area over which this pressure is applied, and the number of passes will significantly affect the compaction in the field. Now discussing the common tests which are performed in the field to check or verify the compaction of the soil. Sand cone method, ASTM designation is given, rubber balloon method and nuclear density will be discussed in our today's lecture. Now starting with the sand cone method, following steps are performed. First of all, we need to fill the jar with a uniform dry sand, Ottawa sand, and call it as W1. Ottawa sand is a standard sand with the known unit weight, density and also specific gravity. The weight of the jar, the cone and the sand filling the jar is noted down, and that is known as the W1. This is the cone, this is the jar, and here Ottawa sand, uniform Ottawa sand in whitish color is shown in this figure. Now we need to excavate a small hole in the area where the soil has been compacted. W2 will be the weight of the moist soil excavated from the hole. W3 will be the dry weight of the soil, and we can find out the moisture content by placing a chunk of soil into the oven, and after 24 hours you can check the change in the weight of the soil, and that change will be reflected as the moisture content. Now in order to find out the W3, which is the dry weight of the soil, so you can use this equation where W2 is the weight of the moist soil excavated from the hole and W in percentage is the moisture content. We can recall that the water content is the weight of water to the weight of solids. Now the cone with the sand filled jar attached to it is inverted and placed over the hole. We dig this hole and then we will invert the sand filled with jar, and the Ottawa sand, we will open the valve. The Ottawa sand will fill this hole. Now the combined weight of the jar, the cone, and the remaining sand filling the jar will be known as the W4, and the weight of sand to fill the hole and the cone is W5. Weight of the cone is usually given because the volume of the cone and the sand is uniform Ottawa sand. So W5 is W1 minus W4. It's the before use and after use Ottawa sand in the jar and cone. V is the volume of the excavated hole. That's what we need to find out. WC is the weight of sand to fill the cone, which is given. Unit weight of the sand, of the standard sand, is also given. W5, which is the weight of sand to fill the hole in cone, minus the weight of cone, will give us the W3 divided by the gamma D of sand. Now we find out the volume of this hole. The dry unit weight of compaction made in the field is determined as W3 divided by V, and W3 is the dry weight of the soil. This is the dry weight of the soil. So here is the W3 divided by the volume. The volume we obtain it from here, so we don't need to use this equation. So we can use this equation, W3 divided by V. This is the weight of dry soil. The volume which we obtained from the W5 minus WC. WC was the weight of the cone. V, volume of the hole. Weight per unit volume will give us the gamma D in the field. From the rubber balloon method, as you saw in our previous method, the sand cone method, we need to find out the volume of the hole. If you dig a hole in the soil, we will collect the moist soil and we will put it into the oven, and after 24 hours we can dry it up and we will find out the W3. And how we need to find out the volume of that hole. So another method, or similar to sand cone method, is also given, except that the volume of the hole is determined by introducing a rubber balloon filled with water from a calibrated vessel. So any change in this vessel will give us the volume of the hole by inflating the rubber balloon in that particular hole. So we already know the dry weight of the soil. We can find out the volume of the hole as well. In nuclear density meter, density or the unit weight and the moisture content is determined based upon a probe which is inserted into the soil. That probe has a radioactive source which will emit gamma rays and fast neutrons. Now, the denser the soil, fewer gamma rays will be detected by the receiver. Now, the wetter the soil, the fewer fast neutrons are detected. Now, dense soil absorbs more radiation than the loose soil, and it measures the weight of wet soil per unit volume and the weight of water present in a unit volume of soil. Now, the dry unit weight of compacted soil can be determined by subtracting the weight of water from the moist unit weight of soil. Instead of digging a hole, if you just insert a probe into it, you will get the unit weight and the moisture content readings. Standard test method is also given for the in-place density and water content of soil and soil aggregate by nuclear methods. Now let's solve a problem related to the sand cone method. We perform lab test in stage 1, moisture content readings for a clay silt, and the dry unit weight from lab test is given. Then we do the stage 2 compaction of the soil, and after stage 2 we went for the stage 3 field unit weight determination or test performed on the same soil by means of the sand cone method. So this is the stage 3. We need to verify the compaction in the field. So the calibrated dry density of the Ottawa sand is given. Calibrated mass of the Ottawa sand to fill the cone, which was WC, is given. Mass of jar plus cone for use is also given. Mass of jar plus cone plus sand after use. This is the before use, 7.59 kilogram. The mass of jar with cone and sand after use, which means that the Ottawa sand has gone into that hole. Mass of moist soil from the hole is 3.006 kilogram, and the moisture content of the moist soil is 10.2%. Now we need to find out the dry unit weight of the field, and we need to find out the relative compaction, because we can plot this and we can get the gamma D max in the lab. Approximately it's 18.9. We can plot that as well, and then we can find out the gamma D max in the lab. So we need to find out the dry unit weight in the field, and we need to find out the relative compaction in the field as well. Starting with the part A. So mass of sand used to fill the cone, it's 7.59 minus 4.78, which is the before use and after use. So this is the mass of sand used to fill the hole and the cone. Mass of sand used to fill the hole, you can see, please subtract the WC from the mass of sand used to fill the hole in cone, and that would be 2.265 kilogram. Now we already know that the dry density is equal to mass per unit volume, and volume can be equal to mass by the rho d density or dry density. So we'll come up with the volume of the whole. Now the moist density of the compacted soil, so the mass of moist soil divided by the volume of the whole. So this is the mass of moist soil, and here we got the volume. We can find out the moist density of the compacted soil. Now, the moist unit weight of the compacted soil can be found out. This is the moist density of the compacted soil, and if you multiply with the 9.81, gamma is equal to rho into G, and if we do the necessary calculation, the unit conversion, we can find out the moist unit weight of compacted soil. Now we find out the moist unit weight of the compacted soil, which is this you can call that as bulk unit weight or the moist unit weight, which is 20.45, and we were given with the water content 10.2. So we will come up with the gamma D in the field, 18.56 kilonewton per cubic meter. The results of lab compaction test are plotted. Find out the gamma D max in the lab will be equal to 19, and gamma D in the field is 18.56 kilonewton per cubic meter. And if you compare these two unit weights, you clearly see that 97.7% is greater than 95%. Hence, the compaction is okay for that particular layer. Thank you very much, and I hope you are enjoying our lectures and videos. Please kindly like and subscribe to our YouTube channel for more videos. Thank you very much, and Assalamu alaikum and Allah Hafiz.